Work, power and energy. Our next chapter is work, power and energy. Work done. Work done. Work is said to be done. Work is said to be done if the point of application of force undergoes displacement under the action of force. If the point of application of the force undergoes displacement under the action of force. Whenever force is applied on a body, then if the point of application gets displacement, then work is said to be done. Work done can be computed in two ways. It can be computed as the product of the component of force in the direction of displacement and the displacement. It can be computed as the product of component of force in the direction of displacement into displacement, or component of displacement in the direction of force into force. To understand this, take the first figure. In the first figure, the force F is acting at an angle theta with the direction of displacement S. The component of force F in the direction of displacement is F cos theta, and the displacement is say S. Then the work done is F cos theta into S. Take the bottom figure. Here the F is acting at an angle theta. Then the component of displacement along the direction of force is S cos theta. The component of displacement in the direction of force is S cos theta. Hence, work done can be computed as F into S cos theta. F into S cos theta. So, the work is Fs cos theta. Fs cos theta. Actually, work is defined as the dot product of force and displacement. It is written as W is equal to F bar dot S bar. W is equal to F bar dot S bar. If force and displacement are in the same direction, then theta is 0, cos 0 is 1, hence W is equal to Fs. W is equal to Fs. If the force is making an angle theta, then W is equal to S into F cos theta or F into S cos theta. Like this we compute the work done. Actually, it is defined as the dot product of force and displacement, which is written as W is equal to F bar dot S bar. Zero work done. Even though force is applied, then there will be no work done in certain cases. Work done will be 0 in the following cases. 1. If displacement is 0. By the application of the force, if the displacement is 0, work done is 0. Or if the applied force is 0, work done is 0. Or if theta is 90 degrees, the work done is 0. Let us try to understand these three cases. Displacement is 0 can be understood when we apply a force on a wall. By pushing a wall, it won't move. The displacement of the wall is 0. Hence, work done by the force on the wall is 0. Work done is equal to 0 if F is 0. If no force is applied, no work is done, even though the body is having displacement. Even though the body is having displacement, if there is no applied force, then the work done is 0. Work done is also 0 if theta is 90 degrees. If the force is applied in one direction and the displacement is perpendicular to it, then the work done is 0. We can cite the examples of a man carrying a load on his head. If he walks horizontally, then the work done by him against gravity is 0. This is shown by the upper figure, two arrows. Horizontal arrow represents displacement, vertical arrow represents force. So that is the force applied by a man, and the horizontal vector represents the displacement of the body, which is carried by a man walking on a level surface, horizontal surface. So here the work done is 0. So also in the case of centripetal force, the work done is 0. The centripetal force acts perpendicular to the displacement. See the circle. The centripetal force is towards the center of the circle and the displacement is along the tangent. Since this centripetal force and displacement are perpendicular, the angle theta is 90, cos 90 is 0. Hence, work done is 0. So, work done is 0 in the case of centripetal force. Work done by a varying force. So far we have studied the work done by a constant force. Now let us take the case of a varying force. If the force is varying and if the force is a function of displacement, then the force will be written as Fx. The function Fx represents the force. That means force is changing with displacement. Then if you draw a graph between displacement and force, if you draw a graph between displacement and force, then you will get a curve which is above the x-axis. The horizontal part of the curve is the relation between force and displacement. And the force at x1 is given by the left vertical arrow. The left vertical line in the graph represents the force when the displacement is x1, and the right line, vertical line, represents the force when the displacement is x2. And the displacements, the force is not the same in both the cases. During the path, it is changing. It is not horizontal. That means the force is not constant. It is a varying force. Such a force is represented by Fx. The work done by this force is calculated using the calculus, using mathematical form in the calculus, which is written as W is equal to integral Fx dx. W is equal to integral Fx dx. Using this formula, we calculate the work done in the case of a varying force. The work done is given by the area between x-axis and the curve. From the graph, the work done can be calculated by computing the area between x-axis and the force curve. Joule. Joule is the unit of work. We can understand joule as follows. We have the relation W is equal to Fs if the displacement is in the direction of force. If the displacement is in the direction of force, then W is equal to Fs. Using this relation, we can define work done, or joule. The unit of work done, joule. Suppose if 1 Newton of force is acting on the body, and thereby the displacement of the body is say 1 meter, by the action of a force of 1 Newton on a body, if the point of application undergoes a displacement 1 meter in its direction, then we say the work done by the force is 1 joule. 1 Newton into 1 second. This is 1 joule. So, if 1 Newton force displaces a body in its direction by 1 meter, then the work done is 1 joule. Like this we have to understand joule.